Hi everyone, my name is Kenny Yu, and in this session I'll be presenting Twine, a unified cluster management system for shared infrastructure. Before I talk about cluster management systems, I want to give a bit of background about how our infrastructure works. Whenever someone uses one of our company's products like our mobile apps, they're making requests to many of our services in our data centers all around the world. This map shows the locations of our data centers. Each pin represents a data center region, which consists of multiple data center buildings in close proximity. If we zoom in into one of these data centers, you might see something that looks like this. Globally, we have millions of machines hosting thousands of diverse services, including web, ads, cache, and more. We need cluster management systems to help manage all of our services and machines to improve hardware and operational efficiency. Cluster management systems assign workloads to machines and manage their lifecycle. Twine is our cluster management system and has been running in production for the past 10 years. Over the past decade, we made 3 key design decisions that distinguish it from other cluster management systems. The first decision is that we dynamically partition machines in a data center region instead of using static clusters. This helps us improve efficiency and perform fleet-wide optimizations. The second decision is that we support customization in shared infrastructure, where shared infrastructure is a common pool of resources that can run any workload. This is in contrast to private pools, which are siloed pools of machines dedicated to individual workloads. Our goal is ubiquitous shared infrastructure. We want to consolidate as many of our workloads as we can onto shared infrastructure to improve efficiency. Lastly, we use small machines instead of big machines to achieve better power efficiency globally. To better understand our first decision, let's explore the following question. What if we use Kubernetes? Many of you might be familiar with Kubernetes, which is an open source cluster management system. We would hit several challenges when we try to run Kubernetes at our scale. The first challenge is that a single Kubernetes cluster can support only up to 5,000 machines. We have millions of machines globally, and this would result in thousands of isolated Kubernetes clusters. Typically, machines are statically assigned to clusters, and this can result in inefficiency. In this example, machines 6, 7, and 8 in cluster 2 are underutilized, while cluster 1 is at capacity. Even though these machines are free, jobs in cluster 1 cannot easily use them because the jobs are bound to individual clusters. We call this inefficiency stranded capacity, and this is a result of static assignment of machines to clusters. Ideally, a cluster management system would make it easy for job owners to reuse available capacity wherever they might be. What if instead of static machine assignment, we can make machine assignment dynamic? Twine uses this idea to avoid stranded capacity. Twine introduces an abstraction that we call an entitlement. An entitlement is a logical grouping of machines that represents a quota of resources granted to a business unit. Machines can be added or removed from an entitlement, like machine 3 in this example. Jobs are bound to entitlements instead of clusters. And within an entitlement, tasks of different jobs can stack together, like the red and gray task in machine 1, representing tasks of different jobs. Any free machine can be used by any entitlement in the region, and this is how we avoid stranded capacity. Note that avoiding stranded capacity is just one example of more general fleet-wide optimizations we perform. As another example of fleet-wide optimization, suppose we just finished construction of a new data center in the region. Ideally, we spread tasks of a job across multiple failure domains to improve fault tolerance and reduce the capacity buffers needed for fault tolerance. In this example, Twine improves fault tolerance of the yellow job by assigning machine 5 from the new data center to entitlement 2. This is automatic and requires no effort on a user's part. Fleet-wide optimizations are more effective on larger scopes, and we run these optimizations at the region level. To support fleet-wide optimizations at the region level, we need to scale our control plane to be able to manage all the machines in a region. As we add more machines and workloads to a region, we shard our Twine scheduler, where each shard manages a different subset of entitlements in the region. Here, shard 1 manages the first 2 entitlements, and shard 2 manages entitlement 3. The Twine scheduler shards and our front end collectively present a single entry point for a region to Twine users. The Twine scheduler manages the lifecycle of workloads and is analogous to the Borg master and Kubernetes controllers. So how well does Twine scale? Each point in this figure represents a production scheduler shard and its P99 CPU usage and machines managed over the course of 1 week. As you can see in this figure, we have shards that manage close to 200,000 machines already, and we can add more production scheduler shards as needed to scale to larger regions. In some of our regions, we anticipate reaching 1 million machines. Larger deployments of cluster management systems introduce new risks, and we identified 2 key risks. A failure or bug in the control plane at this scope can have catastrophic consequences for all workloads in a region. The second risk is that network partitions within a region introduce new kinds of failure scenarios. To mitigate these risks, we employ several design and operational principles. For example, all of our components are sharded and replicated to improve availability and reduce the risk associated with a single instance or shard of that component. We designed our components so that tasks can continue to run even if all components are unavailable. Many of our components have built-in fail-safes to rate limit destructive operations. This reduces the risk if one component has a failure or a bug. Our data center networks have network redundancy to reduce the probability of a network partition within a region. For more principles, please refer to our paper. As we increase in scale and the number of machines we manage, efficiency becomes more important. This leads us to our next design decision. We support customization in shared infrastructure instead of supporting private pools. Large organizations often organize their capacity in 2 ways. With the private pool approach, they set aside capacity for different services or product groups to use. In this example, we have a private pool to run machine learning workloads and another one to run web workloads. However, a service owner may customize these machines to improve performance or other characteristics of their services, and this makes it difficult to reuse machines for other workloads. Here, even though machines 6 and 7 are available, they cannot be easily reused by other workloads because of the heavy customizations. In contrast with shared infrastructure, any machine can run any workload, and we can reuse available machines 6 and 7 to run other workloads in the shared pool. Our goal is to operate ubiquitous shared infrastructure and consolidate as many workloads as we can into shared infrastructure to improve efficiency. This decision introduces several challenges. The first challenge is that many applications may obtain performance wins through heavy host customization. So what is host customization? In our fleet, a small number of services dominate our capacity consumption. These large services often tune host settings to run more efficiently. For example, our web tier achieves 11% higher throughput through a combination of various settings, including enabling turbo, using huge pages, and more. Other host settings services might set include kernel versions, NIC settings, and file system settings. Sometimes one setting might be beneficial for one service and may be detrimental for another. This customization is at odds with the shared infrastructure, where any machine should be able to run any workload. To address this, we dynamically reconfigure machines as needed by workloads. To do this, Twine users can associate a host profile with their entitlements. In this example, entitlement 1 specifies a host profile that sets a specified kernel version, enables huge pages, and turbo. Entitlement 2 specifies a different kernel version and NIC settings. When we move machines between entitlements, we automatically reconfigure machines to have the appropriate host settings for that entitlement. This allows us to maximize the performance of the services running on these machines. So what is the overhead with switching host profiles? On average, a machine changes host profiles once every 2 days. This figure shows the P90 switch time for various host profiles. On the left, we see that a turbo host profile takes 3 seconds, which is negligible compared to the switch every 2 days. On the right, we see that the huge pages host profile can take 240 seconds. This long time is because sometimes we have memory fragmentation, and allocating huge pages may fail, and we may have to reboot the host to finish the operation. We have been addressing this and have submitted patches upstream to the Linux kernel to increase the success rate of allocating huge pages. What triggers host profile changes? For us, autoscaling is a key driver of host profile changes in our fleet. Many of our services are autoscaled and follow a diurnal pattern. The load of these services are correlated with the number of active last-minute users of our products, or ALM. We call these ALM tracking services. In this figure, As the load on our ALM tracking services increases from hour 3 to 10, we reconfigure host profiles on these machines to run these workloads. As the load starts to decrease starting at hour 12, auto-scaling frees up these machines, and we reuse these machines to run non-ALM tracking services. This figure shows the power of shared infrastructure and how it makes machines fungible to improve efficiency. In summary, we addressed a host customization challenge with host profiles. Our second challenge with supporting ubiquitous shared infrastructure is that tasks are not homogeneous, especially for stateful or sharded services. In this example, we have a job running a sharded service with 4 tasks. Each task hosts a different subset of shards of this application's data. This service needs at least one replica of each shard up at all times to ensure availability. Now suppose task 4 becomes unavailable because the machine failed. The job owner starts a soft release now. Cluster management systems are typically unaware of the application's data placement, and it may naively choose task 1 to restart first for the release. As a result, shard C is now unavailable, as all replicas of that shard are unavailable. Since applications know their data placement best, ideally the cluster management system can collaborate with the applications to handle lifecycle events, like software release or rebalancing events to perform fleet-wide optimizations. To do this, Twine provides a TaskControl API. Each application can implement their own task controller, and this figure shows one example of a task controller. If a job specifies a task controller, the Twine scheduler will notify the task controller to decide which operations on task to perform and which ones to delay. In this example, the task controller keeps track of the sharded services data placement and which tasks are unavailable. Let's walk through an example of how a task controller orchestrates a software release. At time S0, the job owner starts a software release. Twine scheduler will notify the task controller that all 4 tasks need to be restarted for the release. The task controller sees that task 4 is unavailable, and to ensure shard C's availability, it cannot restart task 1. It can either restart task 2 or task 3, but only one of these because they overlap in shard B. It decides to update task 2. In the next time step, the scheduler notifies the task controller that the operation on 2 is complete and requests that the next set of tasks to update. The task controller sees that task 4 is still unavailable, and so its only choice is to update task 3. At this point, task 4 recovers, and the task controller can update either task 1 or 4 next, but not both because they overlap in shard C. Throughout this example, the task controller helps Twine maintain the availability of the application during the software release, even if tasks are already unavailable for unrelated reasons. In summary, we provide the TaskControl API to support stateful and sharded systems in shared infrastructure. These workload customizations, host profiles, and task control were the key drivers that enabled large-scale adoption of shared infrastructure. TW Shared is our shared infrastructure for compute, and this figure shows its growth since 2013. We introduced task control mid-2018, and this allowed us to start migrating sharded and stateful systems into TW Shared. We next introduced host profiles early 2019, and this enabled our web tier to start their migration to TW Shared without sacrificing performance. And this migration finished in late 2019. The web tier is one of our largest and most important services, and a large spike in growth at the end of 2019 is because of the web migration. As we crossed 50% adoption, we made a decision as a company that all new compute capacity will land only in TW Shared. And this puts us on a path to migrate all of our compute services into TW Shared by early 2022. Workload customizations were the key factors that enabled a successful adoption and support for ubiquitous shared infrastructure. So what does shared infrastructure adoption look like from a service owner's perspective? We present a case study with Product Group X, which is one of our largest and most important product groups. They operate hundreds of diverse services on hundreds of thousands of machines. In a short 9 months, they migrated 70% of their capacity into TW Shared using 800 entitlements, many of which densely stack tasks from different jobs together. Collectively, they used 3 pre-existing task controllers to support their jobs and 3 different pre-existing host profile settings to support their workloads. Workload customization enabled Product Group X to quickly migrate a significant portion of their capacity into TW Shared, and none of these customizations were specifically built for this group. As we've grown adoption of our shared infrastructure, we start hitting other challenges at our scale, beyond improving individual machine efficiency. In their data centers, power is our most constrained resource. Our services have grown faster than a data center build-out. As you can see on this map, many of our data centers are still under construction. This leads us to our next key design decision, whether to use small machines or big machines. To improve power efficiency, we have two options. We can use big machines and efficiently stack workloads together. However, if we don't stack well, we end up wasting power. As another option, we can use more power efficient small machines with fewer resources. For a rack comparison, a small machine rack has 38% more cores and 34% less memory. We decided to use small machines for multiple reasons. A small number of our services dominate the capacity consumption, and many of these large services are already optimized to fully utilize whole machines. Another reason is that historically, resource control was not mature. For example, we have many stateful systems that use local flash for storage or as a cache, and historically, resource isolation for I/O was not ready. Lastly, we are not a public cloud and have no external users. This means that we can influence our internal teams to re-architect their services to fit into less memory if needed. So how much do we save by using small machines? We defined a total cost of ownership, or TCO, of a machine to include the hardware cost, power consumption, and operating expense of a machine over the course of its lifetime in our data centers. We defined a relative total cost of ownership, or RTCO, for a service as the ratio of TCO to run that service on small machines to the TCO to run that service on big machines. The lower the number, the more savings we get from using small machines. This figure shows the RTCO for some representative services in our fleet. As you can see, most services were able to use small machines effectively, but we do see one outlier on the right. This is because this service is memory bound, and we are working to improve the service to fit better in less memory. Fleet-wide, we had 18% power savings and 17% savings in total cost of ownership. Although we did have success in using small machines, we did have challenges. For example, small machines made stacking tasks less effective. Second, most other large companies typically use big machines. And as a result, this required more work for us when working with our hardware vendors to design smaller machines optimized for our workloads. And lastly, there was significant engineering effort to re-architect many services to fit into less memory. In conclusion, we have been evolving Twine over the past 10 years. We made 3 key design decisions that distinguish it from other cluster management systems. We dynamically partition machines in a data center region instead of using static clusters. This allows us to avoid stranded capacity and perform fleet-wide optimizations at the region level. We support customization in shared infrastructure. This has allowed us to support ubiquitous shared infrastructure and consolidate a majority of our capacity into a shared pool of machines without sacrificing workload performance or capability. Lastly, we choose to use small machines to help us achieve higher power efficiency globally. Thank you. I would also like to thank all the authors on this paper and everyone else who contributed to Twine's development over the past decade.